Problem 8 gives us an interesting new conceptual problem. The setting is where a rocket in space, motionless, and the rocket has a mass of capital M. The only propulsion the rocket has is the velocity of steam it's putting off, and the mass loss per time is capital C, and that's not a unit we usually see. We'll talk about it in a second. And we're looking for the rocket's acceleration in terms of those variables. So first off, the assumptions we need to know is that there's no force due to gravity. We're in space. The Earth isn't pulling on us. We're not going to pull into the moon or anything like that. And then second, the initial velocity we're going to use is 0. From there, I just wrote out the variables we were given. So this first line right here, that's the force equation we usually use when we're talking about Newton's second law. But that's not exactly accurate to all situations. It's not even originally what Newton's second law was. It's just kind of what we synthesized for most common situations that you guys see. The second line is more accurate to what Newton's second law can show in more inclusive situations. So instead of and we'll show how we derive this first one in a second. So what really is Newton's second law is the derivative of mass times velocity. And so you have to take a partial derivative, and if you take the partial derivative, you're left with this. So in most situations when you're applying a force to something, there's no mass loss to that. If I'm pushing a block, the block doesn't lose any mass. So this component right here, mass divided by time, or right here, it usually goes to 0, and you get left with this component here. dv dt is acceleration, so acceleration times mass equals your force. That's the common situation we see on Earth, and we're doing lower level physics that you usually are responsible for. But this problem is asking you to think a little bit outside the box. So using this knowledge and this equation, which is a little more inclusive, we're going to basically analyze this rocket. So we know the force of the rocket is going to equal the force of the steam that is propelling it, right? Those are the only two forces that we have. And we know this equation to be true because of Newton's third law. Essentially, the action being taken by the steam is what's applying the opposite but equal action, also known as forces, on the rocket itself. So we have this equation, and we know that our force is going to equal this above equation. So we can draw this out a little more explicitly. We're going to have dm dt, velocity of rocket, plus dv rocket over dt, times mass equals dm dt v steam plus dv steam dt times mass. The masses are all the same, and this is because it's the same system, right? It's just the mass of the rocket that's changing in every situation. So from here, we can analyze and simplify. So the velocity of the rocket at the beginning is 0. We know it starts at rest, so that component's going to go away. dv dr is acceleration of rocket times mass. So we're solving for this acceleration of rocket right here. And that equals dm dt, which we know is c, so this is basically mass loss over time, times vs, which is another component that we know and a variable we can leave in there. dvs dt is the acceleration of the steam times mass. That is 0 because we're given a constant speed. So there is actually no acceleration of the steam itself. So that goes to 0. So we just get left with this equation. We can very quickly simplify the acceleration of the rocket, which what we're looking for is equal to cvs over mass of the rocket. And that's your final answer.